Swayam Prabha. Digital India. Educated India.
Define common knowledge through this definition. An event A is said to be common knowledge in the state of the world omega star for all I1 IR say in we have omega belongs to ki1 of ki2 kir, sorry, omega star belongs to. Okay, so what does this mean? That it means that I1 knows that I2 knows that IR knows A. Okay, in state of, so in omega star they I1 knows that I2 knows that IR knows A, and this is true for all such sequences that you can create. Okay, all right. No. So this is the definition. It will turn out that it reduces to something much simpler in certain cases. Okay, so we will discuss that in subsequently. Okay, let us take another extreme example. Okay, let's take the example let's take the event B. Okay, the event B is that the Paul is not colorblind and the purple car has won. Or let's say, okay, let's take a different color. Let's take Paul is not colorblind and the red car has won. So now, what does the knowledge operator say about Paul? So when does Paul know this event? When does Paul know that he is not colorblind and the red car has won? It's B itself, right? Paul will know. So Kp of B is actually equal to B itself, because when he is not colorblind and the red car has won, he does know that he is not colorblind and the red car has won. What about John? So when does John know that Paul is not colorblind and the red car has won? Empty set. He will never know this, right? You can check this. There is no element of the partition which is completely contained in set B, right? So this is in fact empty. So what this also means is therefore that this is also empty. Therefore, that means there will never be a state of the world in which John will know that Paul knows that he is colorblind and the red car has won. Okay, so there is no state of the world in which John will know that Paul knows that Paul is not colorblind and the red car has won. Yes. Not necessarily. Yeah. So but this is just again an example. Yeah. So this is an example. This is a very simple case because the states are and the partitions are also kind of trivial in this case. But it doesn't. This is not the only way in which it will happen. It could very well happen, for instance, that this is that this here is not empty, this one is also not empty, but this is empty. Okay. So, John will know something about the event. Okay, there will be some states of the world in which John will know the event. There will be some states of the world in which Paul will know the event, but there will be no states of the world in which John will know that Paul knows the event. Is this clear? That could very well happen. All right. Now let's look at a few properties of the knowledge operator, because this is such a important and useful tool. So here's the first property. For any event and any player, you always have Ki of A is a subset of A. For any event A and any player I, Ki of A is always a subset of A. This means that, so the left hand side here is the states of the world in which player I knows A. Okay. So whenever player I knows A, that state of the world is always a subset of A, which means for player I to know A should have obtained, right. So A should have occurred or obtained. So player I knows A implies A has actually occurred. Okay. So what this effectively means is that the knowledge of the players get knowledge of things when as a consequence of some physical reality. It's not what is knowable in principle, but what has actually happened, and therefore they have come to know. Okay. So their knowledge, the player I's knowledge of A is as a result of A occurring. Okay. So therefore, so whenever player I knows A has actually occurred. All right. So this is therefore a different, this framework, as I had mentioned at the start, that this is more of a control theory type of model, because you know of an event after it occurs. It's not about what could have been known or what could be knowable. Okay. So control theory is always causal, and that's how that is the way this model is also built. Okay. Okay. So this is quick proof of this. So omega belongs to Ki of A, which means basically that Fi of omega is a subset of A, but Fi of omega is the element of the partition that contains omega. So but omega is always in Fi of omega, which means omega is in A. So we start off from any omega in Ki of A, we get that omega must be in A. So now let's suppose I gave you two events, A comma B. These are both sub events. Okay, and A is a subset of B. Right. So A is a subset of B. What does this mean? That whenever A occurs, B also occurs. Okay. So A is more specific than B. B is more general. So whenever A occurs, whenever A has occurred, B also occurs. What does the knowledge operator then say about knowing A and knowing B? Yeah. So whenever you know A, you would also know B, right? And this is, so for any player, Ki of A would always be a subset of Ki of B, necessarily. Okay. Now suppose, so let's take any event. Okay. Now this is the event that player I knows A, and this is the event that player I knows that player I knows A. How are these related? So player I knows A and player I knows that player I knows A. What is the superset? So it's really incredible. You get this for free. You get that these two are these are actually equal. So our way of modeling, I told you again that this is a kind of a physical way of modeling things, because as a result of this, Okay, self awareness comes for free. Okay, whenever player I knows an event, he also knows that he knows that event. Okay, this is a consequence of the Wave model. This could have limitations, but on the face of it, for example, loss of memory, absent-mindedness, and so on cannot be will not satisfy something like this. So, if you have a device that has finite memory, it may know something, but may not know that it knows something, and so on. But you will see later that this is general enough to model a whole lot of other things also. Okay, so this is this is the self awareness of a player you get for free from here. Okay, some more properties. Let's what is ki of y? It's y, right? So every state of the, what does this basically say? In every state of the world, every player knows that something has happened. Okay, so what one consequence you get for free here is that y is common knowledge, because ki of y is y, and this is true for every player. So therefore, every player knows that every player knows that every player knows that something has happened in every state of the world. Okay, all right. Suppose A and B are two events, then what is this? Player I knows that A has occurred, player I also knows that B has occurred. So when player I knows that A has occurred, player I knows that B has occurred, he can put 2 and 2 together and knows therefore that A and B have both occurred. Okay, so we can therefore, we are not proving this, this is very easy to prove. I'm skipping the proof. So this is all, so the knowledge operator also satisfies this. Okay. First tell me, I'll just write this out. You tell me if there is any, what is the difference between these two? What is the difference between ki of A, the whole complement, and ki of A complement? Okay. So this is just again just for clarity. The left hand side is the set of states of the world in which player I does not know A. Okay. So so now the right hand side is the states of the world in which player I knows that A has not occurred. Okay, these are two very different things. Okay, so therefore there is no obvious relation between the two. You can of course say one thing, which is, erase this. This is in fact equal to is actually equal to this. So when player does not know something, he is not ignorant of his own ignorance. He also knows that he does not know. Okay. So again, as I said, self awareness sort of thing comes up. So ki of A is ki of A the whole complement is equal to ki of A the whole complement. Okay. Yeah. So does not know, okay, does not know is a slightly again, so when we start discussing these subjects, the English language is a little bit insufficient, because what does it mean to not do? When I say I do not know means I can for sure say that I cannot confirm that A has occurred. That is what this statement is saying. But the question he is asking is, does ki of A complement mean that I does not know A? Is the states of the world in which I does not know A, or is it the states of the world in which he may or may not have may have not known A? Yeah. So the does not know. So any partial knowledge in this model there is no partial knowledge. If you know, and if you do not, if it is not true that you know, then you do not know. Yes, but in that case he does not know. That is what that's our definition. So there is a more subtle model which we will do after this, in which there is a probability that he assigns to each event. Okay, that's what is called a belief. So from knowledge you can move to beliefs. Okay, in which a player basically assigns a probability distribution on the probability distribution on the states of the world, and therefore on an event and so on. And there you can have these kind of graded sort of levels of knowledge. So their knowledge becomes belief with probability 1. Okay, but we'll come to that after we have done with this. Yes. Why is the last property true? We can show this. So I'll just quickly write out the proof here. So if omega belongs to ki of A, sorry, no, it does. It's not sufficient. The complement is outside, no. So of course you would have this. The claim is not about this. Yeah, so this let's just do this 1 second. So you have your A, and then you have your Fi of omega. Fi of omega is not a subset of A. That means it has some elements which are outside. Now these elements which are outside are therefore elements of A complement. So Ki of A is a subset of A. So Ki of A complement is a superset of. So I think it should follow from the first one. I'll just have to write it out properly. So it's Ki of A is a subset of A, which means this complement is a superset of A complement, and so one of this. Ki of A is a union of, yes, Ki of A is all of these. So in this case is the union of elements of a partition, correct. Some other partitions, that's right. Correct. So I mean this I'm just trying to see if it can be derived as a corollary of this. So there is I'm sure the result is true, and in the reason for that is this only, that see whenever the knowledge, the events when I should have picked a different color, the states of the world in which player I knows A, okay, that means Ki of A will necessarily be either all of Fi of omega or none of. Okay, that is how it will be. You will never have this sort of part in Ki of omega, Ki of A. Okay, for any event A, because because if this is included, then this would also have to be included, but then this is not in A. Got it? The nearby point which is in the same partition, same element of the partition, but is not in A, would also have to be included. So only this part gets included, and then, but I am trying to see if I can just apply one of these inclusion relations and derive this, but it seems like that is not possible. Anyway, we'll do a much more complicated version of this subsequently, in which this will come out for free. Actually, we'll write out the entire structure of this. So I'll just remind me, I will do this proof in class. Okay, so actually let's do a quick property, another property of common knowledge. Okay, let's come back to common knowledge and let's do one theorem related to it.